Okay, let's get started. So, just before I forget, to make sure I don't forget, I posted the review sessions on the course website. This was just TBA for a while, and we did have one, the TAs had one last Tuesday, is kind of a one-off. But now this is our regular schedule throughout the whole semester each week, every Monday, Tuesday, Friday, 4 to 6. So right after this lecture, and on Tuesdays, 4 to 6, you have review sessions. Several TAs will be hosting these review sessions, so if you want extra reinforcement of the content, or you want to hang out with the TAs, whatever. You have these review sessions. They'll have presentations prepared. You'll also have some time to ask some questions and everything. So please take advantage of that. We have lots of review sessions this time around, 6 hours a week, so take advantage of that. Make sure you're hitting them. Office hours are posted. The schedule is still a little bit in flex as the TAs figure out their schedules, so I'll be updating this periodically. We have the office hour schedule, which will be outside of Davis 302. If you go to the third floor of Davis and you're facing the elevators, turn to your left and walk all the way down that hall. The TAs will be in that common area down there. In my office hours, I'll be in my office, Davis 344, Tuesdays 1 to 3, so if there's something where you need to see me for, you got some paperwork for me or whatever. Or it's Tuesday 2 to 3 and nobody else is on, come see me. Review session locations as marked. Any questions about this? We have lots of resources available for you to get extra help in this course. And always Piazza and all the other resources as well. Okay, so let's clean up a little bit of content that we didn't finish last time. Talk about some data structures. So data structures in Scala, I won't spend too much time. A lot of this is going over syntax. But just like I did with types, I will go a little bit deeper into each data structure just to explain a little more of what's happening. I won't go too deep. A lot of this is going to be CC 250 material, but we do want to be able to use a few of these data structures. So there are lots of them in Scala. This is what we call an inheritance tree. That'll make more sense as we get into object-oriented programming. But I just wanted to kind of flash this as a preface to that, and also show you that there are lots of data structures that you can use in Scala that I won't necessarily talk about in class. A few of them I might mention as they come up, as we have a good use case for them. Like a set, I have some examples that use that, I believe. But we're going to stick to just a couple, mainly list and map in this course. But let's talk about these three. We've already seen array, so I better mention that one as well. Array and list are sequential data structures, just like list in Python. Array in Scala, they're going to behave how we would expect those to behave. And map is our key value store. Excuse me. So arrays, these are sequential. This is a sequential data structure, meaning there is a fixed order. Like there is a well-defined order to these. And for an array, this is a continuous block of memory that's sectioned off for each element. So for example, the element at index 0, and they're all indexed. The element at index 0 is right at the start of this array. And then the next element, we're going to skip ahead however much memory it takes to store one object of the type that we're storing, skip ahead that much, and then that's going to be the location of the next object in that array. So we have this nice mathematical formula to be able to figure out the exact memory address of an element at any index. So given its index, I can tell you exactly where it is in memory and jump directly to it. This is what we call random access. It means I can just access any element of this array very quickly, just with one multiplication, one addition, very cheap operations, get directly to that element. This, however, is a fixed size data structure. An array cannot change size. Once I have this memory allocated, say I want an array of size 5, I need my element size times 5. I need that much memory, and it has to all be one big continuous block of memory. So the next memory address on my RAM stick might be used by another program, might be used by another variable in my program. We don't know anything about it. We can't say, hey, operating system, give me that exact memory address, because it might be already used. So we can't just increase the size and extend this block, because it has to fit in with everything else that's running on our machine. So you create an array, it has to have a fixed size. You have to specify its size immediately, and that cannot change. A lot of languages will simulate the size changing if you append the end of a JavaScript array. it will create a new array with the larger size and delete the old one to get around this limitation. But an array cannot change size without without deleting it and creating a new one. Here's some syntax for an array. Not too much to talk about, except this top one. I'll talk at length about this in a second. Assigning a value and getting a value, it's notation you would expect, except instead of square brackets, we have parentheses for these. These are function calls. Iteration, just like we saw when we talked about loops. And we have a few ways to iterate over the indices. If you want the indices of an array, iterate over those indices. So say for some reason you need the indice, the location of an element with a particular property. Maybe you're finding the min element and you need to return the index of that, like we did in 115. You can either use the to method that we already saw. 0 to array.length is going to give you all those indices, 0 to the length. Should that be length minus 1? I must have tested this, but anyway. Or as a little bit of shorthand, you do have access to array.indices, which will give you exactly what you're looking for. It'll be a data structure containing the indices. I'm questioning myself on this one just because I never do it like this anymore. I just use .indices. If I'm sure it's fine because I must have tested this. But anyway, iterating over the indices, you can also do it like this. But the one I want to talk about right here, Scala is strongly typed, and this applies to our data structures as well. A data structure, when we create a Scala data structure, it can only store one type of element. So when I create this array, I can't just say, give me an array, like we did in Python, like we did in Scala, Python lists, in JavaScript arrays. We can't just say, give me a list, give me an array. We have to specify its type. Because in those languages, we can mix the types. You could have a Python list, add an int to it, add a float to it, add a string, add another object. You could add a function to that list. You can add anything and mix your types as much as you want in that language. Scala will not let us do that. We have to have our types absolutely specified. So when we create a data structure, we give it a parameter called a type parameter with this notation to say that this is an array of ints. This array, after I create it and say it's an array of ints, and Scala will look ahead and this array that's created will be an array of ints because I'm assigning it to this variable. This array can only store ints for its entire lifetime, and this variable I created, ARR, can only store arrays of ints. I can't reassign an array of doubles to this variable, and I can't put a double in this array that was created. I can't mix my types at all. The types have to be fixed. This is an array of ints. It can only ever store int values. So that's the big difference, this type parameter. Our data structures have to have these type parameters. List, a bit different than an array. It's still sequential, so there's a fixed order, a meaningful order to this data structure, but it's not one continuous block of memory. So with a list, and specifically a linked list, which Scala lists are based on, and we'll talk about it later in the semester, is the elements of this data structure are chopped up all across memory. They can be anywhere on our RAM sticks that the operating system decides. It'll just allocate memory wherever it wants. The way we structure a list to be able to get the actual structure in our data is we have a reference to the first element in the list, and the first element has the memory address of where the second element in the list is located. So if I want to traverse a list, say I want the fourth element of a list, I only have access to the first element. I say, hey, first element, where's the memory address for the second element? It'll say, oh, it's over here. I'll go over here, I'll read that, I can read the data if I want, and then say, hey, where's the memory address for the third object in this list? It's over here. Okay, I'll go over here. Where's the fourth element? Go to that memory address, and then I can read that fourth element. So I don't have this very quick random access anymore where I can just jump right to the fourth element. I actually have to navigate all of these nodes and ask each element, hey, where's the next one, to be able to get to that element. So this can get more very expensive, very slow, inefficient operations if we're not careful. Again, as I mentioned last Monday, we're not too concerned about efficiency in this class, so we'll get away with it. I'll say, In 250, you'll dive way deeper into these topics and talk about all the optimalities that we can make in our data structures and how we use them. But one advantage of having our data spread across memory like this is we do get variable size. So if I want to add another element to a list, I just go to the last element of that list and say, hey, I created this new element over here. Your next memory address in the list, you should go point to this thing over here. So we can easily add to a list without affecting, without running into other memory issues, running into other memory that's allocated for other uses. And these cannot change in Scala. We'll also talk at length about that as we go through the semester. So here's our syntax for a list. Some of it's the same as an array. Creating a list, same syntax. We're just using list instead of array. To get the first element, dot head is going to give us the value of the first element in that list, which we always have access to immediately. And then if we want to pretend that our list is an array and pretend that our elements are not scattered all over memory and that they're indexed, we can use this apply method. This apply method is inefficient. Again, we'll get away with that in this course. But this apply method is going to say, give me the element this far away from that. So this would be give me the second element, which we can kind of think as the element at index 1, but there's no real concept of indices in a linked list. Iteration is the same as we would expect. We just have some data structure here, same syntax. These two I want to talk about quite a bit here. So this trips up a lot of students, a lot of people just learning Scala. Lists are immutable and their values are immutable. Nothing, which means nothing can change in this list. I create this list that has the values 2, 3, 4. Once that list is created, it cannot change ever, at all, in any way. This list cannot change. So I'm storing this list in this variable named list. If I do want to make a change, I'm going to use the syntax for appending an element to the end or prepending an element to the beginning. I'll call one of these operators and add 50 to the end of this list. What this actually does is creates a brand new list with the elements 1, 2, 3, and 50, and leaves my 2, 3, 4, and 50, and leaves my original list completely alone. So list is storing this value of this list here. I'm going to call a method on that list to append 50 to the end of a list. It doesn't affect the original list that I called, but it creates a brand new list with 50 appended to the end. So now I have two lists in my program, but where we have to be careful, and the question we'll still see, no matter how much I stress this, me and the TAs will still see it in office hours, just fine, is you have to reassign this to the variable. So list is no longer pointing to this list, which still exists and still has been unchanged, it respected immutability. But when we created this brand new list with 4 elements, we have to reassign that to our variable. So now our list variable is storing the new list, not the old list that we had. So we're reassigning to the list. We always have to reassign back to our original variable. Same with prepend. We're creating a brand new list with a new element, 70 in the front. We have to reassign that to list. If you don't have this assignment and you're just saying 70 prepend to list, you're going to drive yourself nuts saying, where is 70? It's not in my list. Why is it not in my list? Well, it's because you created a new list, but you didn't do anything with it. You just left it on the floor and didn't assign it to anything. So that new list was returned, but since you never stored it in a variable, you have no access to it anymore. You just compute it, leave it there, and then move on. Well, list is still pointing to the list that you created before. So make sure you reassign. Whenever you're modifying a list, you're actually creating a brand new one, and then make sure you reassign it back to that variable. Yes, question?
Can you append to the array?
No. So an array can't, so the question, can you append to an array? Nope. An array can't change size. You can change the values at certain indices, but you can never expand the size of the list because you'd have to get that next chunk of memory. And that chunk of memory, we don't have any guarantees that it's available, so we can't expand an array. Any language that lets you expand an array, they're actually creating a brand new array and just doing that behind the scenes for you. You can't actually expand an array. Yeah.
So can we create a list contains a bunch of array?
Yes. So, question, can you create a list that contains a bunch of arrays?
Yeah.
Yes, you can nest these types as much as you want. We could create a list of arrays, of lists of maps that we'll see next. You can mix and match these however you want, and you can have, this type can have like 18 different nested type parameters. Any place that calls for a type can be a type that has type parameters. We usually don't want to because it makes the code less readable, and for that, what we'll see on Friday, we'll create classes and create objects based on those classes that contain those data structures. It helps organize our code a bit better, so it's more legible. But we certainly can. Yeah. There's another question. Is that answered? Go back here.
How do we remove an element from the list?
You remove an element from the list. I don't remember the exact syntax off the top of my head. If it's dot delete, I don't remember the syntax off the top of my head. But there is a way to do it for sure. That, again, will return a brand new list with that element removed. Yeah, I don't remember off the top of my head. It's going to be something like remove or delete. I just don't know. Okay, one last data structure for today, maps. These are our key value stores. They behave the way you would expect them to behave from Python and JavaScript. Their keys have to be unique. You can't have duplicate keys and the such. You can't, I don't know, they just behave like you would expect them. They're technically based on hash maps. They're built on hash maps in Scala. That's a bit too far for this course, but that's a 250 topic that you go in depth in. And I'll mention efficiencies. I already mentioned efficiencies of data structures a few times today. I'll mention them in passing and so forth, but we won't focus on it too much in this class. CC 250 is where you'll dive into all of that. CC 250 is going to dive deeper into the data structures we'll see in this course and that you've already seen. And they'll talk about all the trade-offs between these data structures. So like an array, we have fast access of the values and we can change the values, but we can't change the size of an array. A list, we can change the size, but we can't access like the middle element of a linked list very efficiently. 250 is going to talk about all those trade-offs and when to use what data structure based on your particular application. So you're going to get very strong doses of this next semester. In 116, we'll stop at how do we use these data structures. So the three that we're seeing today, and then trees and graphs as we get later in the semester. How do we use them? 250 is going to talk about what's the most optimal way to use them. So just to specify the difference between these courses, where we stop and where 250 picks up. So a map, we have our key value store. Again, we need our type parameters, but a map will take two type parameters. We can specify the type of the values and the type of the keys separately. So this is a map of int to int, but these types can be different. So we're not constricted to just one type in the map, but every key has to be the type parameter of the keys, and every value has to be the type parameter of the values. So this is a map of int to int, and I have to respect those types. Scala will hold us to that. It won't let us put any different types in this map. The syntax for a key value pair, we're going to use this right-facing arrow, similar to iterating over a data structure where we use the left arrow. We're going to use dash greater than for this one. So I'm storing these three key value pairs. Here are my keys, 2, 3, and 4, and my values 4, 9, and 16. These are going to be the key value pairs stored in this map that I created. And I mentioned, I was thinking mutable map. Technically the hash map has these properties, but we are using, by default, it'll be immutable maps, and that's what I'll use for the assignments. When I say map, I mean immutable map. When I say list, I mean immutable list for this. So when we do change a map, we can add a key value pair like this, We do, just like the list, have to reassign it to our variable storing that map. We are creating a brand new map. So we do have to reassign with maps as we did with lists. If we add a key value pair with a key that's already in the map, if I wanted to add 3, 10, it's going to overwrite this one. I can't have that duplicate key, so it's going to overwrite my old value if I try to duplicate a key like that. If I want to access a value, I have a few options. I can use this shorthand with just parentheses, where it kind of looks like an array access with square brackets, except we have parentheses as it's this being a method call. We could use .get instead if you want to be a little more verbose. Or we can use get or else. This is going to give us the value at that key, and if that key is not in the map, it will give us whatever we give it in its this second parameter. So 100 not being in this map, this is going to return -1. Then on the next line of code, I could say if y equals -1, handle this in whatever way I want to handle that missing key, however I want to handle that. If you don't use get or else, if you just use .get or the parentheses syntax here, this accessor syntax, and that key is not in the map, it's going to crash your program. So just something to be aware of. If you're not positive that the key is going to be in there, use get or else so your program's not crashing. You don't want to crash. You want to be able to handle those errors, handle that however you want to program it. And iteration, a little bit different here. I could do mymap.keys, mymap.values, and do what you would expect in Python. You can do those, but Scala gives us this nice syntax where we can iterate over the keys and values at the same time with very little overhead. The syntax is really clean, it's nice. For my money, why would I ever iterate over only keys or only values? I'm going to iterate over both at the same time. And if I only need keys or only need values, whatever, I just won't use the other variable. I think this is the cleanest way to iterate. With this syntax, iterate over keys and values at the same time. You don't have to, it's whatever preference you want. I think this is for my money, I like iterating over them like that, instead of using just keys or just values. All right, any questions on these data structures? Like I said earlier, that it's a lot of syntax. It's going to take a little while just to get used to all the new syntax. You have to look up things a lot. And clearly with delete, you and I have to look these things up every once in a while. We're computer scientists. We don't like to memorize things. There are a lot of references out there to look up the syntax. Which I'm sure you'll all be doing on the homework assignments. Looking up the syntax and just getting used to working in this new language with these new data structures. Similar data structures, but new language. Whoa, that's not what I want to show. This is the one I want to show. Okay, so with that, we've come across our first learning objective. So today marks the beginning of our program execution learning objective. So the next 2 weeks, these 6 lectures, these are all going to be about program execution, and then the following week will be your lab for this learning objective. So what are we going to learn for program execution? Really, how does a program run? And also testing. What we'll introduce today is how to automate the testing of our code by writing unit tests. Then we're going to start talking about how to handle references with linked lists. I talked about kind of memory addresses and references quite a bit. We're going to dive into that and talk about what that means and what that means to us as developers. What do we have to be aware of when we write our programs when we can be passing objects as references to our methods? What does that mean to be pass something by reference as opposed to pass by value, which we'll also see. And to go along with that, how is everything stored in memory? We're going to see that a program splits its memory into the stack memory and heap memory. What does that mean? What variables go in the stack? What variables go in the heap? And how do these references, these last two are pretty linked, but how, when an object is stored on the heap, what does that mean for us and how the memory is stored for the program? And also when we we'll talk about stack frames, calling a function, how does that work, and how does the scoping work? If I have a function call and certain variable names in there, just very briefly. A function call, say I have a function with a parameter named x, and I call that from a main method where I also have a variable named x. How does the program know when I say x, what x I'm referring to? And we'll talk about stack frames, which is the answer to that. So let's get started. Oh, not quite get started on this. One more thing I want to talk about. The first homeworks are out for this learning objective, for the application objective. So much terminology I introduced here, but for the first application objective associated with this learning objective, we have two homeworks. We're fine-tuning the write-ups just a little bit, but they're pretty well ready to go. So they're released to you. You can take a look at what the homework assignments are for this application objective. And just a reminder, I know I talked about this Monday, but that was a while ago, and I want to make sure this is abundantly clear to everybody. This is a choice. This is an or operator. Either do physics engine or rhyming dictionary. So I, of course, encourage you to read through both descriptions, get a feel for what each assignment is asking you to do, but choose your favorite one, or what you're probably most of you are going to do, and I can't really stop you, is choose the one you think is easiest, whatever. You're going to do what you're going to do. Choose whatever one you want to do, and then work on that assignment. You don't have to do both. You can switch at any time. If you run into a roadblock and you're just really sick of one of them, try the other one out, go for it. But only one of them. You don't get any extra credit if you do both. So you can do both if you feel like it, but from the course perspective, I'm not going to care. I'm going to treat that the same as if you just did one of them. This week's lab is, if you haven't had lab yet, most of you haven't, is setting up your IntelliJ environment. You should all have it set up at least to be able to do last week's lecture questions, but making sure it's going to be set up to work for the rest of the semester. Make sure it's working for all the libraries that we're using. You're going to run Maven to install those libraries, and then run some of the code from late in the semester, just to make sure all your versions are compatible, just everything is all set up perfect with that. Then next week's lab will be setting up the homework assignments and getting started on those. But please don't wait till that lab to get started on the assignments. At the very least, read the documents for them and know what we're talking about. And you can get started on those much earlier than that lab, especially if you have a Friday lab. I would not want to wait till next Friday to start the assignment. All right. Any questions on that before we rip into unit testing? Cool. Okay, unit testing. So lecture question for today. We're going to look at the lecture question from last Wednesday. This is exactly the lecture question from last Wednesday. But we're going to write a test suite to automate the testing of this to see if the compute shipping cost method is properly implemented for any implementation of it. So we want to write the unit testing for this. So what is that and what is testing? What are we talking about here? So there's kind of an evolution to testing that I think most students go through, kind of the natural evolution that we expect you to go through for testing. First, number one, you start in 1.15 and you're asked to write some code in UB Infinite. You bang out some code and you click the submit and you see if you get a green bar coming back from UB Infinite. If it does, hey, your program worked. But your testing is pretty much looking at your code and just saying, yeah, that looks right to me. After that, or you submit to Autolab. If it's an Autolab assignment, you submit to Autolab. Autolab says you did good or you did bad. And that's your kind of first phase of testing. And hopefully around halfway through 1.15, I hope, and I really hope everybody's here by now, you get to the point where you start testing your own functions, method in this case, where you'll write a main method in Scala or in Python, JavaScript. You just call your functions, print the results to the screen, and manually verify, okay, did this compute what I expected it to compute? This is kind of the second level of testing. It works in a lot of cases. It'll suffice. And it's far better than just submitting and checking your grade. That's probably the worst form of testing that we have to wean you all off of. This is the beginning of weaning you off of that. So call the method, print the result to the screen, verify with your eyeballs that the answer is correct. But what happens when you have a very large project? One of the big themes of this course. What happens when you have a large project, hundreds of files, thousands of methods, hundreds of thousands of lines of code? What are you? Those would be big files. Maybe not hundreds of thousands, but a large project. What happens when you have a very large project and say you have a method in your project that you want to update? You want to rewrite this thing because maybe it's not as efficient as you want or whatever. You want to rewrite this method, and this method is called all throughout this project. You have many, many modules, many methods that are calling this and that depend on it. How are you going to test that and make sure you didn't break anything in this code base? You're not going to go to every single file, run every single main method that you wrote, and verify with your eyeballs that it printed out the right thing to the screen. You're just not going to do that. If you are, you should probably be fired if you're on a team. You shouldn't be developing like that because you're going to be spending a week just verifying every change you make. So we want to automate this process. This idea of call the method and check to see if it returned the right thing, that's what we want to automate, and that's where we're going to use unit testing. We're going to use unit testing to automate that process. So unit testing, we have our automated tests. Each test is going to have a lot of checks that it does. We'll see there'll be assert calls. We're going to set up the test, and then if every one of our checks passes, then our code is good, and we pass the test suite passes. If any single one of our checks fails, even if it's one out of thousands and thousands, our test fails, our code has a bug in it, and our test is going to scream at us and say, hey, I got a problem over here. You better get in here and fix this bug because we can't go to production. We can't show this to our users with this bug in here, or else people are not going to like our software. We're going to have bugs. It's going to be a problem. So any one of those fails, the whole code, the whole project fails. So we need every single test to pass. And we also want enough test coverage to make sure that we're checking for all the possible bugs. So if our unit tests just don't check anything, we're going to always pass our unit test, but we might have very buggy software. So let me just throw you a test in Scala. This is the structure of how we're going to test our code. So with this, we're going to use the Scala test library. This is something that doesn't come with Scala. It's not built into Scala. It's not part of IntelliJ. You don't have it, unless you've been to lab already. You don't have it on your machines. So we need to download Scala test and link it to our project. We'll talk about that towards the end of lecture. But first, let's see how to use this and what we're going to use it for. But we have to download Scala test to be able to get this import. This Scala test will be read, and you'll get errors. IntelliJ is going to yell at you if you didn't download the library first. So this import will give you the errors if you haven't done that. So let's write a test suite using Scala test to test one of the examples from last week, that compute size method that just had some boundaries and checked whether a value was large, medium, or small. So first, this is more boilerplate, similar to the main method. This will make a lot more sense as we get later into the semester, specifically object-oriented programming. But for now, we're creating a class named whatever we want to name it. And for the assignments, when I say create a test suite named whatever, this is what I mean. This name should be changed to be whatever the name of that test suite is. This is the name of our test suite for this functionality. And then extends fun suite, which is not as fun as the name implies. Fun is short for function. We're going to test the functionality of something using this fun suite. A side note, I didn't mention this in the other lecture, but you don't have to use fun suite as long as you're extending something in the Scala test thing. If you want to do some behavioral testing, the Scala test documentation sets you up with something that's not fun suite. If you want to use that, and you know what that is all about, you're welcome to do that for the assignments in this class. If that doesn't make sense to you, just use fun suite. And then we're going to set up our tests. That shouldn't make sense to anybody yet. I don't even know why I said it. Anyway, then we're going to set up our tests. We're going to use the syntax test. We're going to give it one argument. This is going to be the name of our test. It can be whatever you want. Just something descriptive or not descriptive. I'm not going to hold you to it. But something that describes your test. And then the body of the test. What are we going to test? The body of this can be any code that you want to run. You can set up any variables, create any data structures, whatever you need to do to test your functionality. And then we're going to call the assert methods. These are the important parts of the test. This is where we're actually testing. If we don't have any assert methods, maybe we forget to add them, your test always passes and you're really not testing anything. So each assert call is going to take a Boolean expression and it's going to check if that Boolean is true or not. If this Boolean expression resolves to true, that test passes, that part of the test passes. The assert passes. If it's false, the assert fails and the entire test suite fails. So if all three of these asserts are true, this test suite is going to pass. If any one of these is false, the test suite fails. It means I did not implement compute size properly here. So for each one of these, I'm going to say, okay, call my compute size method on some value, 70 in this case. Calling that on 70, I expect that to return true. The expected behavior is 60 or larger is going to be large. 30 to 60 is going to be medium, and below 30 is going to be small. That's our expected behavior for this. So I would expect 70 to be large, 50 to be medium, 10 to be small. If those are all true, I'm happy. This test suite passes. I'm feeling good. The second parameter is a string, but Scala will call toString for us, so I can throw doubles in here and it'll do the conversion for us. It'll call toString. The second argument is a string that's going to be displayed if the test fails. These are optional. You can leave these off and just give the Boolean. But if the test fails, these will give you a hint as to what failed. Here I just want to print out the input. It's going to say, hey, this test failed. And it's going to say 70. And I'll be like, oh, it failed on input 70. That means 70 didn't return large. So I better go look into that. If you don't have these, what we call hint text, hint strings, if you don't have those on there, Scala test still gives you, it tries to be pretty helpful about the feedback it gives you. So you still get some information, but if you want more information, use that second argument. Give it that second argument to be able to print more information to you. Which brings us to our big question. First, any questions about setting up a test suite? Like the theme for all last week, it's mostly syntax. You can treat it mostly as boilerplate, and then the assert is the big part to know. But any questions about that? Yes?
Will it show you like which test failed or?
Yes. So once one of these fails, Scala test will tell me the line that failed. It'll actually throw an error and crash the program. So if this first assert fails, the other two don't even get ran, and it says error on this line. So then I can go right to that line. I know that assert failed, and then I can get all my information here. So in this specific example, this doesn't help me, but in a few examples from now, we'll see where that comes in handy. But it will tell me the line number that failed. Just to foreshadow a little, when I have an assert inside a loop, that doesn't always give me the full picture. Okay, so the big question, question. Will it always be 3 times? So you can have as many asserts as you want for that. I just happen to have 3 here, but actually the next example will end up having 4, and then we'll expand that even more. Which brings me to the question, is this enough testing? Should we have more than 3? I'll reverse that question. Yes, we should have more tests for this one. That should be unanimous. We need more testing. So a reminder, here's the correct solution, and this is the expected behavior we have. So where the problem description, if I were to assign this one, I'd say write a method that takes in a double and returns large if that double is greater than or equal to 60, small if it's less than 30, and medium otherwise. It'd be something like that. That would be the question. Here's a correct solution, correctly implemented, has the boundaries 60 and 30, everything's good. We're happy with this. This is the correct solution. And it passes our test suite. It's going to handle these, our test suite is going to pass this correct solution just fine. But here's an incorrect solution. This is wrong code. This should fail my test, but it passes the test suite that we wrote. So the boundaries are off, but just by the 3 values that we chose to check, our test suite is still passing this code and saying, yeah, you're good. But this code is broken. This is bad code. This is buggy code. It's not going to, if we're using this to weigh packages and figure out what to do with large, medium, and small packages, it's not going to do its job. We're going to have the packages mixed up if we're using this code in a scale at the post office, for example. So let's add some more test cases to our test. Let's just check a few more things and make sure we're getting right up against those boundaries. We want to check those boundaries and make sure that we're having the cutoff right at 30 and right at 60. So I want to go right at 60, right below 60, right at 30, and right below 30, and make sure I have the right cutoffs for each one of those. Now we're checking those boundaries a lot better. Now, is this enough testing? And this is a question that'll go throughout your careers. When are you confident that your code is correct? Yes.
So like, I don't know which one it's called. I'm pretty sure it's like something large. So like, if you just do a loop and like iterate from 0 to 100, but like if you did that and the loop fails somewhere and it goes wrong, would you get to know like where it failed, like that number, or would you just be like in the loop the error at
Yes. Yeah, great question. So say we set this up and had a loop that tested like all the values 1 to 100, and say one of those values, one of those tests failed, but I have my assert in a loop. It's just going to tell me the line number of what failed. This is where we would want to use, and actually my next example will hit on this a little bit more. This is where we definitely want to use the hint text. So in this text, we put the value that we're testing for that specific iteration of the loop. Then instead of just saying, hey, your test failed on this line, it's going to say, it failed on this line, and here's your hint text that you gave me, and it's going to be that exact value. Now I know, okay, on that input, this assert failed. So it would be a good application of that hint text. Does that get to your question? Sort of? All right. And you want one loop that's going to test like all the values 1 to 100? So, because at some point you have to check, like, you have to code the boundaries in there. Okay, I think I see where you're getting at. You want the test to be very comprehensive. You want to throw a lot of values at it without too much code, right? Is your goal? At some point you have to code those boundaries. And this is one thing that we can get into with testing, where we don't, sometimes it's hard to avoid, but we don't want to get into a situation where for our testing, we're recreating the functionality of the method that we're testing. And we'd have to do something like that in that case. If we're just looping 1 to 100, we have to have some conditional. If this value is less than 30, expect small. Like you'd have to have some logic like that. Is this getting at your question? Maybe we can talk after lecture a bit. I don't want to get too sidetracked, but we can chat. So the question with this one is this enough testing? This is a question, I mean, you write some software, you test it. At what point are you happy with it? And you say, that's enough testing, I'm sure there's no bugs in here. I'm ready to ship this to my customers. When do you stop? This is always a big question. It'll be a question throughout this semester and throughout the rest of your careers, all the software you write. When are you happy with it? When are you confident it's right? With this test, if we have a compute size method that passes this test without seeing the code, without knowing what the actual implementation of that method is. If it passes this test, are we going to say, yes, that method is implemented correctly? And at this point, probably. This is probably good enough testing. This is a question we all have to ask ourselves, especially after you graduate. When do you stop testing? This is pretty good. You can always add more test cases, but you're checking the boundaries. You're not getting overboard with the testing, but you got a decent number of tests. I think most of us would want to add at least a couple more just to make ourselves feel good. And with this question, the question itself doesn't define what should happen with negative numbers, but we could clearly define that in our behavior and then test for that. What should happen with a negative number? With the problem definition, it says less, which I never actually showed, but less than 30 should return small, so technically negative numbers should return small. But what if I have an implementation where I'm, for some reason, taking the absolute value of the weight, so negative 100 would end up returning large? Might want to check for things like that. But those are more edge cases. Out there in the real world, you have that actual physical scale. You're not usually going to get a negative rating. You should still handle it, but you know, when is this enough testing? For this problem, probably enough. But we can go further. If we want to do more testing, we want to be more comprehensive and absolutely be sure that we have the right functionality. We want to do something like this, and I like this example because I want to show an application of the data structures we just looked at. So here, instead of just having a couple of hard-coded examples, I'm going to have some lists where I'm going to store a list of every value that I felt like testing that should return large. Then a list of all the values that should return medium, and a list of all the values that should return small. I'm going to do my negative testing here. I'm going to make sure those negatives are returning small for this. And just for good measure, I want to show one application of appending to a list. When I have, say later on, I think of one more value I want to test for larges, and for whatever reason I didn't just feel like putting comma 10,000 here, I can append to the end of large doubles, but always remember we're changing an immutable data structure. We can't change a list. It only creates a new list, so we're going to reassign it back to large doubles to add that extra test case. And now we're going to iterate over those data structures and have our assert check for each one of those one at a time. So here's where we would get to the case where, okay, if one of these fails, Scala tests is just telling me a line number, okay, this assert didn't pass. Well, that doesn't really help me because I have a lot of different values. Here's where my hint text comes in. I'm going to take that variable and put that as my hint text. Now it's going to say this line failed, and you told me to tell you this number, and it's going to say, oh, failed on 90. I'm going to be able to use that hint text to be able to figure out what exactly went down with that failing assert. And the same would be true for the other ones here. What failed and what input specifically failed. Now we have more comprehensive testing. We should be, if we were a little paranoid about the previous test, we should be feeling quite a bit better with this one. I think if you write a method that passes this test suite, you should be feeling pretty good about your code. Shit, I didn't realize how late it was. I didn't get to the Maven demo. I'm not going to be able to jam it in. To get Maven, if you look at the 1 p.m. lecture at the end of that video, you'll be able to get the Maven tutorial. Because you will have to install Scala test for the lecture question today. So run your Maven, go to Maven, click this. With your pom.xml and your root directory, you can get there. That's a very quick version. But with that, I'll see you Wednesday.